So here's another example. We're going to factor this thing. Now, hopefully from here you can see, remember, you always want to get the GCF first, right? Well, hopefully you can see from this that the GCF is going to be 1. Well, again, that's because there's a non-zero constant term. So you can't factor out x out of every term. Not only that, since there's a coefficient of 1, the only factor in common among 6, 1, and 7, that is the only factor in common among the coefficients, and the constant term is 1. I mean, I hope that makes sense what I just said. But basically, you can't factor out the GCF, is what I'm trying to say. I mean, because it's just 1. Okay, so what do we do? Well, we're going to use the AC method, right? We have 3 terms, a trinomial. The degree is 2. And also, the leading coefficient is 6, not 1. So what do? We are going to use our AC method. I wrote over here, as you can see, I changed subtraction to addition. You don't have to do that, but when you get the coefficients, you have to remember to include the negative. That's what I'm doing. So in this case, we get our A is 6. We get our B is just 1. C is -7. And remember, you get A times C, which in this case is -42, and B is still 1. So from this method, what do we want? We want 2 numbers whose product is -42 and the sum is 1. So 2 numbers whose product is -42 and the sum is 1. You might be able to see what those what numbers would work. I mean, 6 and -7 won't work because their sum is -1. But what about 7 and -6? That'll work. You know, again, it's just like when we first saw factoring, that is, these trinomials. You know, sometimes you have to play around a bit. So 7 and -6 work. Their product is -42, and their sum is 1. Okay. So again, what we're going to do here, let me go back first. We're going to replace then, right, the coefficient 1 here. We're going to replace that with 7 plus -6. Excuse me, we're going to replace it with -6 plus 7. We're going to replace it with a sum. And when we do that, we're good because we're distributing the x, just like in the previous example, right? That's how we get 4 terms. Now, you might be thinking, wait a minute, couldn't you just use 7 plus -6? You could have. The reason I chose -6 plus 7 is that the second and fourth term now have the same sign. And we have addition in the middle. So you could do 7 plus -6. You might need to do a little more work, but not much more. Either one's right. Either way, what we get is a polynomial with 4 terms. So what do? Factor by grouping. Now, I think I might have skipped a step by mistake, but although you might be able to see right away that this polynomial with 4 terms, the GCF is 1. So let's handle each of these individually. So here we have 6x squared minus 6x, right? That's the first group we're dealing with. Okay, so what is the GCF here? What's the greatest common monomial factor of this? Well, the smallest exponent of x is 1, as we can see. And here we have 6 and -6. Well, they have the same factors. So because of that, the greatest common factor of 6 and -6 is just 6. 6 and negative 6 have the same factors. Factors can only be positive. So our GCF for that is this. And as usual, figure it out. Okay. Again, I'm showing division. If you don't show division, that's okay. I just want to make sure you can see enough steps so that everyone understands. And when you write out the work for me, just show enough steps so that I know what you're doing. Okay, that's good. Okay. So that was the first group. Okay, so the first group, we got 6 times x times, x minus 1. Now we handle the second group, which is 7x minus 7. So let's handle that thing. Well, it's just like before. There's a non-zero constant term. So the greatest common monomial factor of this, that's going to be, it's not going to have an x in it. 7 and negative 7, no. They have the same factors. Right? If you were to list them, you would get just 1 and 7. So 7 itself is the greatest common factor among 7 and negative 7. So the GCF here, in other words, is 7. We factor that out. There we go. Okay, and as before, you put the number in front to figure out what's left over. In the background, you're dividing. Although some people can actually see visually that you would peel the 7 off from each term. But, I just like to include division. Okay. That's good. So from each of these two groups here, we end up with this. So we have a common factor for both, x minus 1, as you can see. And that's good. We want a common factor because then we can take it out. And that's what we're doing here. So the x minus 1, we're pulling that out, as you can see. Okay. Right? And again, when you divide, you have to divide into each term. There will be cancellation, so we get this. Right? As you can see, you divide into each term. Here, this cancellation, and you're left with this. So that's what we get. Again, what I remember, in this middle, we had 1, and we replaced it by negative 6 plus 7. If you replaced it by 7 minus 6, that's okay. If you do everything correct, you're going to get the same answer. I mean, maybe the order here might be different, but that doesn't matter. Okay. All right. So let me just let me see. I just want to finish up. Here, I just want to present some vocabulary. So basically, whenever you factor an integer, right, there's always at least one way to do it. 1 and the integer itself. Well, with polynomials, you could do the same thing. You can always write a polynomial as 1 times the polynomial itself, or negative 1 times negative the polynomial itself. Those are what we call the trivial factorizations. For any polynomial, you can factor it that way. Maybe I shouldn't say that because those factorizations aren't helpful, which is why we call them the trivial factorizations. When you factor something, the whole point is, one of the main points is, you're breaking the polynomial down into more manageable pieces. But the trivial factorizations, they don't do that. They don't have that. Now, it turns out in certain polynomials, the trivial factorizations might be the only way to factor them. They might be the only way to factor them. It's just like with, with certain integers like 2, right? You can only factor 2 as 1 times 2. That's it. Such polynomials are called irreducible. And there are many examples of that. For one, if you have something like this, where you want to try the AC method, but the AC method doesn't help, meaning there are no numbers whose product is A times C, that add up to b. Then this is irreducible. Or to be a little more concrete, you can have something like this. A and B are non-zero. They don't have any common factors other than 1. It turns out these will be irreducible. You can't break them down any further. In particular, if we take A to be 1, you get this. We have x squared plus b squared and x plus b. Those are irreducible. You can't break those down any further, other than the trivial factorization. So we have polynomials that are irreducible, and if a polynomial is not irreducible, it's reducible. In other words, you could just factor it. Okay. And just like we can do with integers, although you may not have seen why, that's beyond the scope of Math 104. But it turns out for polynomials, you could factor those completely. Again, how do we know we can do that? That's a little bit beyond the scope of the class, of Math 104, I mean. Okay, I think that's it for this. Okay. So let me see. We have less than a minute left, so I think we'll have to stop here. Okay, again, there is homework, and I will post the quiz. I'll let you know when it's posted. Okay, so have a nice weekend.